So now we're going to do a very crash course in function transformations. So we're only going to be concerned with a couple of different ones. Vertical stretches, vertical shifts, horizontal shifts, reflection over the x, and then reflection over the y-axis. Now this is just going to show you each individual transformation, and I'll use a couple different models to demonstrate. So a vertical stretch. Vertical stretch would be something that increases the stretch of the function, meaning if you're looking at a basic linear equation, think back to the family of functions, y equals x looks like that. A vertically stretched y equals x, vertically stretched linear equation would look something like that. And the manner in which we get there is to add a coefficient. Hold on. Is to add a coefficient. So y equals, there we go, 3x would be a way of doing that, where this multiple, so y equals ax, for instance, that a, the value of a, represents a vertical stretch. So if you're looking at something like 2x squared, we know that x squared looks like this. And if we are vertically stretching it by multiplying by 2, what we're doing is taking x squared, but we're taking those original, so this is x squared, right? We're taking those original values and multiplying by 2, which causes each of them to increase in magnitude by a factor of 2. So something like this, and that would be the 2x squared. So it's vertically stretched. Think like it's been pulled vertically. Now, looking back to linear, you can see the vertical pull here with that multiple, but you can also see a vertical pull this way. It increases the magnitude. So if you think about a negative number being multiplied by a value, it's going to become more negative, or the magnitude, its distance from 0, is going to increase. So in general, if we have a multiple, so if we were looking at y equals the square root of x and we were to vertically stretch it, we would go 2 times the square root of x, which would cause a vertical stretch. If we vertically stretch by a factor of 1/2, which you can see the difference, 2 would cause an increase. Multiplying something by 1/2 causes a decrease. This would cause what is called a vertical compression. So if you're looking at values between 0, we'll use a there, and 1, that would actually be a vertical compression. Vertical shifts. You've seen these before. If you're looking at y equals x, a vertical shift would be +1. What does that do? It causes the graph to shift up literally 1 unit. So the new y-intercept would be that. It can often be the y-intercept. It does not have to be, though, in every case. So if you were looking at a graph of a quadratic that is shifted vertically, that vertical can go up and down. So if I did a -7, what would that mean? Well, y equals x squared in the most basic form looks like that. And if I take that whole thing and I subtract 7, it means all the values are going to be 7 lower uniformly. So you get exactly the same shape, just 7 units lower. So that would be a vertical shift down. In general, whatever the function is, plus or minus some other value, often use b, that would represent the vertical shifts. Vertical shifts work like you expect: plus up, minus down. Horizontal shifts. You've seen these with quadratics, and that's the easiest way to explain it. What would be the difference between these two graphs? So if we're looking at y equals x squared, we know that it has roots and a vertex at 0, 0, right here, right? What is x minus 2? Well, if we think way back to finding roots in a quadratic, that would mean this is x minus 2 times x minus 2, which means it has a double root. We'll talk about that a little bit more later. But that would mean that when the y is equal to 0, the x value is equal to a +2. So it would actually be this graph here. So in general, when we affect, notice how we're affecting the x value before we square it, right? When we affect the x value directly, then we see this shift. Now it is a little bit counterintuitive. this x minus 2 causes a shift to the right, rather than the left 2 units. And if we double check what would happen if I made this x plus 2 quantity squared, that would cause a shift left, because then the root would be at -2. So another couple of examples. If you are looking at something like y equals x plus 3 cubed, that would take on the general shape of a cubic model, so something like that, except it would be shifted. Well, these things work the opposite of what you expected, so it would be shifted to the left 3 units. So it would be something like this. And we know that this point here would be 3. Or if we look at something we're not as familiar with, the square root of, now we're going to affect the x directly, meaning what's inside the square root, like that, right? What would that do? Well, a normal square root function looks like this, yes? So if we actually then take it at x square of x minus 2, when is the y value going to be 0? Happens when x is equal to 2, because 2 minus 2 is 0. So what the effect is a shift, in this case, to the right 2 units. Reflection over the x-axis. This is easy, you've seen this before. What is negative x squared? Negative x squared is this graph that opens down, as compared to y equals x squared. What's the difference? Well, that's our basic parent model. All we do is we throw a negative in. So if you're looking at y equals opposite x, or y equals opposite x cubed, or y equals opposite the absolute value of x, or y equals the opposite, please note where the opposite sign is, opposite of the square root, right? All of these represent reflections over the x-axis, basically throwing a negative in as a multiple. Now you can do combinations. This would cause a reflection over the x-axis, and the 2 is a separate entity, right? Think about it, if I wrote it as a negative, it's really a 1, right? That would actually be then a vertical stretch, and that's where we start to see things kind of bleed together. Reflection over the y-axis. Just like a horizontal shift affects the independent variable directly, the same is true for a reflection over the y-axis. Now this is going to be something interesting. We know that y equals x squared looks like this. Turns out y equals negative x squared looks like this also. Why? Because sometimes when you have graphs, if you reflect them over the y-axis, it doesn't make a lick of difference. Now, there's also some confusing things, but let's stick to one where it's a little bit more defined. What happens when I do this? Well, am I affecting the independent variable, that is the x, directly before I'm then finally determining the y? The answer is yes. To take the square root, I had to have a positive number. So I could take the square root of 0, that'd be fine. Then I could not take the square root of 1, but I could take the square root of -1 now, because negative 1 will be a 1. So what will happen is I'll end up with a graph that'll look like that, and that would be reflected over the y-axis. Now there are certain functions where this is kind of a moot point. Y equals x squared is one, reflecting it over the y-axis doesn't make a lick of difference. Y equals the absolute value of x. If I put a negative in there, it's just going to become positive anyway. So if you think about the graph, if I reflect it, it doesn't change. If I'm looking at a linear model, the same thing happens. There are a couple different models that actually where it makes a big difference, and square root of x is certainly one big one. Okay? And actually, that's all we've got for that. Like I said, this is just a crash course, the basics.